So given a differential equation, we will like to solve it. So the following questions are involved. So what is the solution? Does every differential equation have a solution? If so, how many solutions does it have? Can the solution be expressed in nice form? If it cannot be expressed in nice form, then can you get some understanding of the solution, some way to approximate it, as at least we can visualize it, and how to proceed systematically. So depending on the type of differential equation, we'd like to apply different methods to solve the differential equation or to deal with the differential equation. So the way to proceed in a systematic manner is depending on its order, that is whether it is first order, second order, or nth order differential equation. We have different methods. Similarly, whether it is linear, we have some methods. If it is non-linear, we have to apply more involved methods to solve it. But sometimes solution is not possible. We can only approximate it, or we can plot it, and so on. So a differential equation f x y y dash and so on up to nth derivative of y is equal to 0. This represents a differential equation. We consider that differential equation. We assume that this differential equation is it is possible to solve this differential equation for its highest derivative to obtain the differential equation of the type nth derivative of y is equal to f of x comma y dash and so on up to y n minus 1. And then we study this particular differential equation. Why we assume that it is possible to solve the given differential equation in terms of this differential equation for its highest derivative is that sometimes the given differential equation of the above type may give rise to more than one differential equation of the type below. You see an example. The differential equation y dash square plus x y dash plus y 4 times y is equal to 0 give rise to two equations, namely y dash is equal to minus x plus square root of x square minus 16y divided by 2, or y dash is equal to minus x minus square root of x square minus 16y divided by 2. So you can see that if we treat y dash as a variable, then it's a quadratic here, and so it gives rise to two possible expressions for y dash. And so to avoid this ambiguity, we assume that the given differential equation can be expressed uniquely as a differential equation involving the highest derivative. Now, there are two types of solutions possible. One is called explicit solution and another is called implicit solution. The explicit solution of a differential equation, ordinary differential equation, where the differential equation is written in terms of its highest derivative, namely nth derivative of y is equal to f of x comma y dash and so on up to y n minus 1. So it's a function f of these variables on the interval x between two real numbers alpha and beta. So the explicit solution of this differential equation on this interval is a function phi x such that the first derivative of phi with respect to x, the second derivative of phi with respect to x, and so on up to the nth derivative of phi with respect to x exist, and the derivatives satisfy the equation nth derivative of phi x is equal to f of x comma phi dash and so on up to phi n minus 1th derivative on the interval x between alpha and beta. So for a differential equation given here, if such a function phi exists which satisfy the given differential equation. So what you are doing, we are substituting the various derivatives of phi in the given differential equation, and it holds after substitution. So if phi satisfies the given differential equation, then we say that phi, or rather y equal to phi x, is an explicit solution. We'll see examples of it. Now, it may not always be possible to get an explicit solution on solving a differential equation immediately. What we may get is what is called as implicit solution. So what is the implicit solution? It's a relation g of x comma y is equal to 0. G is a function of x and y. This expression is called the implicit solution of nth derivative of y is equal to f of x, y, y dash, and so on up to nth derivative of y. So g x comma y is equal to 0. This is called an implicit solution of the differential equation. This, if this relation defines at least one function phi x on the interval where x lies between alpha and beta, such that the function phi is the explicit solution of the given differential equation in this interval. So a relation is said to be implicit solution if from this relation we can get an explicit solution. We will see examples of this. Here, x square plus y square minus 25 equal to 0 is an implicit solution of x plus y, y dash equal to 0 in the interval where x lies between minus 5 and 5. Now this is an explicit solution. This is a solution that you can easily verify when you take the derivative of this with respect to y. You will get this expression. So this definitely is a solution of this differential equation, and you want to express this particular expression in terms of y is equal to some phi of x. So what you get is, you can write y square is equal to 25 minus x square. So y is equal to plus minus square root of 25 minus x square. So it gives phi 1 and phi 2 two functions. One is the positive square root, one is the negative square root on the given interval. So we can say that the given solution x square plus y square minus 25 equal to 0 is a implicit solution, because it gives rise to explicit solution, namely y is equal to phi 1x and y is equal to phi 2x. Two explicit solutions are there, which comes out of this implicit solution. In the next case, we will see an example where something which appears to be a solution is not an implicit solution. So consider x square plus y square plus 25 equal to 0. So this expression, if you take derivative, you can easily see that it's a solution of x plus y, y dash is equal to 0. So it should be a solution of that, but we say that this only formally satisfies x square plus y square plus 25 equal to 0, only formally satisfies x plus y, y dash equal to 0. It is actually not an implicit solution of the differential equation, because this expression do not yield any explicit solution. Clearly, x square plus y square is a positive quantity and it cannot be equal to minus 25. So this particular expression do not yield any explicit solution. So this expression x square plus y square plus 25 equal to 0 is not an implicit solution. It's only a formal solution which is not of any use. We consider the first order ordinary differential equation of the form y dash plus axy equal to bx, where ax and bx are functions of x. If bx is equal to 0, then we say the equation is homogeneous. Now, the solution of a homogeneous differential equation forms a vector space under usual addition and scalar multiplication. You can easily see if y1 and y2 are two solutions of a homogeneous differential equation, then alpha y1 plus beta y2 is also a solution. So, the solution space here is a vector space. This is something which uses the knowledge of linear algebra from 106. Now we consider first order ODE in general form, namely capital F of x comma y dash is equal to 0, or in the form of its first derivative of the dependent variable, namely y dash is equal to f of x comma y. We deal with what is called as initial value problem in ODE. So what is the initial value problem? A differential equation along with an initial condition is called a initial value problem, or IVP. Namely, we have the differential equation y dash is equal to f of x comma y, and the initial condition is y of x0 is equal to y0. We'll see examples of differential equations with initial conditions. So given an amount of radioactive substance, say 1 gram, find the amount present at any later time. So since we know a particular kind of radioactive substance, we know the decay constant for it. Now, a initial condition is also given to you. Namely, at time 0, and the amount of radioactive substance is 1 gram. So y0 is equal to 1. That is the initial condition given. The differential equation you can recall from before, that it is dy by dt is equal to minus k times y, where k is the decay constant. So the initial condition here is y of 0 is equal to 1. By inspection, we can say the solution of this differential equation is y is equal to c times e raised to minus kt. You can see that when you take the first derivative of y with respect to t in the differential equation, the first derivative of y with respect to t is given to be equal to minus k times y again. So the y after taking derivative is not changing, it is just getting multiplied by a constant. So this tells us that the solution should be of the type exponential of t. And then you can easily by inspection find out that it is precisely y is equal to some c times e raised to minus kt, where k or minus k is the decay constant and c is some arbitrary constant. Now what happens if the initial condition is given to you is that you can determine the constant c in most of the cases. Now here we take the initial condition c is equal to 1. Sorry, we take the initial condition and substitute it in the given solution. So here if we substitute t is equal to 0, then y is equal to 1. So we get 1 is equal to c times e raised to 0, that is 1 is equal to c times 1. So c is equal to 1. Hence, the differential equation has a solution y is equal to e raised to minus kt, which is a particular solution which satisfies this initial condition y0 is equal to 1. So this particular solution which satisfies the initial condition is not having the constant c.